you enjoyed your lunch and enjoyed the time of meeting with your fellows. Today, we're going to start a session with 3 papers that have a little bit of an application focus to them. The first up is going to be the design and implementation of a parsimonious neuromorphic PID for onboard altitude control for MAVs using neuromorphic processors, and it'll be presented by Stein. So please welcome Stein.
Thank you, Robert. I'm not going to repeat the name of this work, but I'll go into detail into all the separate parts. But welcome, thank you all for being here. I really enjoy being able to present today live. So I'm going to discuss this work. Essentially, it's about a neuromorphic PID, proportional integral derivative controller, to perform control for a micro air vehicle, a drone in common language, using a neuromorphic processor. My name is Stein Stroobants. I'm a PhD student at the Micro Air Vehicle Laboratory in Delft University of Technology in the Netherlands. So our lab is mainly, let's see, there we go. So my lab, what a large part of what my lab does is it draws inspiration from biology or from nature to develop new innovative types of drones specifically. So one of the examples that we have is the Delphi, which is I'm still. There we go. Yeah. So it's the Delphi Nimble. Its latest version, which is a 28-gram flapping wing robot, which is able to fly around autonomously, and which also includes a stereo cam, and can perform all kinds of aggressive maneuvers, such as backflips, for instance. This one is not entirely neuromorphic, but we are also, a part of our lab is interested in neuromorphic systems. Some work, for instance, is about estimating the optical flow from event-based cameras, but also to perform control tasks, such as performing a constant divergence landing with a trained spiking neural network that was trained with an evolutionary algorithm. So the input was ventral flow from images, and the spiking net calculated a thrust set point to perform a constant divergence landing. So the goal with all this, from our part of the neuromorphic section, is to create this fully neuromorphic pipeline that we can use to control a drone. So a fully neuromorphic autopilot. This requires a lot of separate sections. So we need to go from neuromorphic input to neuromorphic actuator output. And there's a lot of separate parts here, such as sensing. So that's what we've seen already today, but also perception, so state estimation or sensor fusion, and decision making. So that's more of a higher level decision making tasks, such as obstacle avoidance or navigation, but also lower level control tasks. And the lower level control tasks are the one that I'm discussing today. So I will very quickly introduce spiking neural networks, but I don't have to do it in depth, I guess. But artificial neurons, they receive floating point values synchronously, or in these snapshots from, as Chiara mentioned them today. And one of the downsides is that, especially in some large networks, there might be parts of the network that are completely almost inactive because they're multiplying and performing calculations with very small values. So one of the biggest, so contrary to these ANNs, we have spiking neurons that don't take these floating point synchronous inputs, but they use these spike trains as inputs and accumulate these in the membrane potential. And when this membrane potential crosses a certain threshold, it produces a spike itself and propagates this further down the network. So especially so the sparsity here and the asynchronously, the fact that they're asynchronous can be very efficient energy-wise. And that's also why currently some industry leaders are also developing all kinds of processes. And we've seen almost all of these today already. So Intel's Louis and Spinnaker, we've heard about them today. And we were interested in the Louis since it has a form factor that we can actually take with us on a drone, which is of course very important if you're working with these energy constrained systems. So that's one of the more interesting parts about drone research right now in this field, is that we think that these methods might help us someday to create all these algorithms that are not available right now for these flying robots. But we are currently still very constrained with the materials that we have. But luckily we can use this USB form factor right now on our somewhat larger drones. So all in all, SNNs, they provide, or at least we think that we can use the benefits of their high energy efficiency, the fast inference, and because they have this inherent temporal dynamics, they can be used for efficient modeling of spatial temporal data, which is of course very important for robotic tasks. And last of all, we draw inspiration from nature, and since these are also very brain inspired, we hope to achieve the same performance that, for instance, a fruit fly has in flying or navigating around a room looking for food. And this makes them all interesting for these robotic applications that we work on. But if we look at the work that I discussed before, where we calculated the thrust set point based on the ventral flow, there's also other parts that need to be addressed. So the thrust set point was calculated from this using this trained SNN, and this was sent to a conventional PID to perform the actual control. So still on a von Neumann CPU, and at some point, if we want to have this full neuromorphic pipeline, we will have to get rid of this as well. So these methods, they require event-based inputs, and we have already seen these this morning as well, so I'm not going into detail here, but we have event cameras that produce events, of course, and tactile. There is also already tactile sensing devices that also produce event-based data. So these examples exist, but still there's a lot of sensors and parts of a drone that actually are not neuromorphic yet. So we need to be able to encode these values into spikes or events. And there's multiple methods of doing this, and I'll very quickly go through a couple of these. So most traditionally is rate coding, which actually uses the frequency of a neuron or a group of neurons to represent the value. And this has been long believed to describe the properties of a neuron in our brain also. But recently it seems to look like it's not that's not the entire story. Another type is temporal coding, where it's not the frequency of a neuron, but the time between different neurons spiking, or the time it takes for first spike to be emitted, is actually describing the underlying value. And the last one, that's the one that that's interesting for our work today, is position coding, or also called population coding. And in this type of encoding, we take a complete population of neurons, so multiple neurons. We separate the input space in multiple bins or multiple ranges, and then every neuron represents a certain part, like one of these ranges. And then at every time step, one of these neurons will spike, and this describes the underlying value. So this is also found in biology, and this is the one that's interesting for our application. So to go to a more deeper understanding of the PID, of how we do this, I'm first going to go back to the leaky integrated fire equations. So these are, we already saw the continuous time ones, I think, this morning, but these are the discrete time versions of the LIF equations that we implemented. Now what we can see is that if we change the time constants tau, so the leak parameters or the decay parameters, If we change them in a range from 0 to 1, we can completely alter the dynamics of this neuron. And in this case, for instance, if we make tau 1, then we just get a complete integrated fire neuron. But on the other hand, if we reduce this value all the way to 0, we forget about all information in the past, and we only take current information from the current time step into account in calculating the membrane potential, and also the fact if this neuron will spike or not. So combined, so this is also what we do in this work. We set these tau values to 0, and then we forget about all info from the past. And combined with position coding, we can now implement multiply and accumulate equations. This is also inspired by work from Stuxnet and others, where they controlled a 1 degree of freedom robot arm UAV with the similar setup. So I think the easiest will be if I explain this with an example. So for instance, if we want to add a value in a range of -2 and 2, and we add 2 of these values, we separated the input range in 5 values. So every neuron in the input range represents a range of 1. And the output range, all the possibilities are, of course, between -4 and 4. So if we now add 2 and 1, then we will see that the neurons 2 and 1 will produce a spike, as it is done in the position-coded way of encoding. And then we have 2 layers that will take these and represent a position-coded sum of these 2. So we have a proportional connection from the input layer to the aggregate layer, where the connection to the aggregate layer, so the top part of the aggregate layer is the positive part, and the bottom part is the negative part. So every neuron has a positive connection to the same value in to all values in the positive part, and a negative connection to all the values in the negative part. So you can see now here that the value 2 has a stronger connection to all values than the value 1. And this will result in a membrane potential of 3, the sum of 2 and 1, in all the positive values, and -3, the sum of -2 and -1, in all the negative values in the aggregate layer. And this means that because we set the thresholds in the aggregate layer also completely proportional to the value that they represent. So for instance, the neuron with 3 in the circle has a threshold of 3, and since all the membrane potentials in the positive layer add up to 3, this means that all values up until 3, or all neurons up until 3, will spike. And the one with 4, the threshold is not crossed, so this one will not spike. And now we have to go back from this, from these 4 values spiking back to a single spike, a position-coded value. So we have a direct connection between the values in the aggregate layer and the same ones that they represent in the reduced layer. So that's a proportional connection. So the connection between 3 and in the aggregate layer and the 3 in the reduced layer has a weight of 3, and the same holds for 2 and 1. But they also have an inhibitory connection to all values below it, meaning that they make sure that these will not spike. So now there will only be one spike, which is the value 3, the sum of 2 and 1, and this will emit a spike that can be used in a different part of the network. So now we have this group of neurons that can actually perform a sum, and we have shown that we can perform addition. But of course, we can also transform this in subtraction, because subtraction is the same as adding negative values. So that's also possible. And we can also transform these into multiply and accumulate by scaling the inputs, the input weights and the thresholds. And then we and another very nice benefit of this is that we can also add more than 2 values. So we can, now I've shown how it works when we add 2 values, but if we add another input, an input group of neurons, a position coded input group of neurons, this will also work in the same way. And besides that, also here I have 2 ranges that are equal. So from -2 to 2 and with 5 values, but that doesn't have to be. They can also be represented by a different amount of neurons. So yes. So then we go to the PID part. Yeah, as was also discussed, this is a more practical part of today's session. I think I'm not sure if everyone is familiar with the PID, so a proportional integral derivative controller. But basically, you add 3 parts. Based on the difference between the set point value and the error. So the error between the set point value and a measured value, and you perform control based on these 3 parts. The first part is just the proportional part, so that's proportional to the error. The second one is proportional to the integral of the error over time, and the last one is proportional to the derivative of this error. So the discrete time equations for PID are shown in the top. So we calculate the error, integral, the derivative. And then lastly, we we calculate the control action U. And as you can see, all of these are basically multiply and accumulate equations. So we can implement the PID with a group of these or a combination of all these neurons that I just described. So the structure, and yeah, so the structure that we used is shown in the image. So normally a drone or a micro air vehicle uses a set of these PID equations. So cascaded PID, which starts, for instance, for position control. So you have position set points. These are transformed into velocity set points. These velocity set points are sent to attitude set points, to rate set points, all the way to rotor commands, to specific rotor commands. And what we did we wanted to show the performance of our controller, and we only used it for altitude control based on a LiDAR sensor. So first we implemented this in simulation, and we compared the response to a regular PID with similar gains. We saw that it was working and it was reaching its set point. So we thought it was time to implement it in a real world scenario with our neuromorphic processor, because that was the goal for us. So the setup that we used is shown here. Most importantly, we gather altitude measurements from a LiDAR that's located on the bottom of the drone. We encode these in a position-coded fashion in ROS, in the robot operating system, and we send them to Loihi, and Loihi, together with the set point, of course. And then Loihi calculates the thrust set point and sends it back, and we send this to the flight controller, and this is then executed. So this video shows a couple of test results. Not really sure if I need to click it now. Okay. Yeah, so this shows the setup again. You can see that what we do is we send a step. This is the step response to a certain altitude set point. So you can see the red band on the top left is the range in the encoded value, because we encode this entire range in only 15 neurons, which means that every neuron represents quite a significant height range. But you see that the drone reaches the set point and then stays within within this red band. So, and yeah, so we tested this for multiple set points, and the thrust command is shown on the left. So for future work, so what we did is we showed that we can use this for altitude control. So theoretically, we can extend this to a complete cascaded PID controller on Loihi, on the neuromorphic chip, so that it only requires, for instance, position inputs and the measurements that we obtain from the flight controller, and we can do the entire control on Loihi. So that's one of the things that we want to do. And one big challenge that we had here is that the derivative that's calculated right now is a one-time step derivative, which means that if you have a short time step and a low resolution in neurons, that a shift in the bins of the neurons or in the population coded neuron will result in a very high derivative at this one time step, and it will result in a zero derivative all the other time steps. So this requires, for instance, to increase the resolution of the neurons to a very large value, because if the resolution is infinite, of course, then the derivative will be perfect as well. But there are some limitations, of course, to the hardware that we have. So we are looking for better ways to perform that, and also we are looking for different ways of developing this PID. So not only with position coding, but also there's also in literature, there's also examples of work that did this with rate coded values. And also what is very interesting, of course, is to have a controller that's actually completely trained with online or offline data. So yeah, so to conclude, what we have now is we have this PID controller, which is just a plug and play block that we can now use in a pipeline of one of our other controllers or entire autopilot setups. So yeah, so this is really a plug and play PID, which is also available. We have the code online, and I'm happy to answer any of your questions if you have them right now.
Thank you very much. I think we have time for a couple of questions. If there's anyone in room 2, if you won't mind coming over to room 1. Is there a question?
So I may have missed it. How big are the implementations on Loihi, like in terms of network size?
Yeah, so the implementation that you saw flying there, it was only 93 neurons. So this is really small. Yeah, but also yeah, there are some limitations in the, as you saw in the bandwidth. So you saw it oscillating a lot, and that's completely because of the size of the network.
So if you scaled it up, you could potentially.
Yeah, so that's what you saw in the simulation results that we have here. That was with more neurons, and then you can see that it actually reaches the set point and stays there. Yeah,
yeah. Thanks a lot. So I was wondering, so if you were to put just a normal PID controller on a microcontroller, what would be the gain in terms of, what would be the neuromorphic gain in terms of energy and delay?
Yeah, so I think that that all depends on the implementation. So I would never recommend someone using a neuromorphic PID if the rest of the system is in a von Neumann CPU, because then you will not win anything, of course. But if the rest of the system is completely neuromorphic, I think the time and the delay that there is between going out of this neuromorphic processor and into a regular CPU is just immense. So if it is possible to have multiple parts in the same network, and especially if they are so small, like only 93 neurons, well, you can fit that almost in any CPU, in any processor, then the gain, I would say, is in not having to go out of this processor and into another one. Yeah.
So this is a question from one of our virtual attendees, Jim Plank. Are there unique features of Loihi that enabled this work, or would just having pretty much any basic LIF neuron do?
I'm sorry, can you repeat the question?
Does Loihi give you anything special here, or would having sort of any basic, you know?
No, this is, no, yeah. So setting all the temporal values to 0 almost gets you there. And then, yeah, the rest is implementation yourself, of course, yes. But no, there's no special Loihi stuff necessary, no.
I've got a question myself. If you wouldn't mind going back to the chart that you showed comparing the neuromorphic PID. So on here, I'm kind of curious, you said one of your future works was to look at encoding. How does encoding impact? It looks like your curves are very close to the PID. Does encoding have any impact here? And you know, did you play with different encoding values to
Yeah.
optimize those curves.
Yeah, so there's two things in here, of course, which holds for all people involved in control know that PID tuning is a very manual intensive work.
It's a real pain.
Yeah, exactly. So that's my background. And tuning in neuromorphic PID is the same. So
Yeah, you almost have tuning on top of tuning here.
yes, yes, but it essentially boils down to the same thing. But then, of course, yeah, the size of the network and the size of the distribution of the encoding also plays a part. So what we also did, I think it's also in these results, is that regularly normally what you do with a position coded value, or what is the easiest way, is to split it up in a linear distribution, where you have a linear distribution of your entire input space. But what we also can do, and especially for control tasks is really interesting, is to have a much more fine distribution around the center, or around zero, around the set point in this case, and a much more like bigger representation of the values further away from that, which means that you can use the same amount of neurons, but still have a much more, yeah, how would you say, like a closer control around your set point. So yeah, we did play around with this, yes.
Is there any other questions?
Yeah, there's just a question popping up from.
This is from Federico Carati. Thank you for the excellent presentation. A question regarding the parameters of the PID. How were the parameters of the controller set? Were they learned? You mentioned in the beginning having an evolutionary strategy for learning the parameters. Can you give us some more insight?
No. So as I also just mentioned, like this is a very manual intense labor, and especially because, and this also holds for PIDs, but when we go to Louis, for instance, then we have to compile the network, of course. So this means that we need to find these parameters, and these are of course different for every drone. And as you saw in the videos as well, this is also different for the battery level of the drone, which can be reduced if you take the battery level into account and all these kind of stuff, all these kind of things. But in this case, we found the parameters by flying it with simply a Python implementation of the network, testing the parameters, and then when they were good enough, we implemented in a Louis code and then flew it with Louis. Yeah, that's the easiest way. And for books on manual PID tuning, there is a lot of it. You can come to me, but that's not it was not necessary for this work. No.
Thank you very much.